Hello and welcome to this lesson for Chemistry 20 in the acid-base unit, part of the solutions acid-base unit. This lesson, we're going to talk about the difference between monoprotic and polyprotic acids and bases. So to get started, we'll talk about the acids first. So like the word would suggest, mono versus poly. Okay? Mono means one, and poly means greater than 1. Okay? Protic comes from the fact that, remember, a hydrogen has a donatable proton. We talked about in the first lesson about acids and bases. Proton being the hydrogen 1+ ion. So, getting into talking about mono versus polyprotic acids and bases, an acid that has only one donatable hydrogen that it will ionize into is called monoprotic. So when you're looking at the formula of an acid, you're looking for how many hydrogens does it have that it can donate. Here, most acids have hydrogen at the beginning. So if there's just one hydrogen at the beginning, it's a monoprotic acid. If it's an organic acid where the H is bonded to the COOs, all of the H's bonded to the carbons there are part of the acetate ion. The H bonded to the O's are the only donatable hydrogen. Okay? So one hydrogen that it can ionize into is called monoprotic. If it has more than one hydrogen, monoprotic acids, by the way, can be strong or weak. And in fact, when we actually looked in the last video at the strong acids, most of them are actually monoprotic. So having more hydrogens doesn't necessarily mean it's going to be stronger. If your acid contains two or more hydrogen ions that it ionizes into, it is called polyprotic. So for example, H2SO4, H3PO4. An organic acid that has two hydrogens is HOOCCOOH. There's two COOs in here, so both of those H's are donatable, making that a polyprotic acid. Now, more specifically, if they have two donatable hydrogens, they're called diprotic, and if they have three donatable hydrogens, they are called triprotic. Now, when you have a polyprotic acid, and it, again, showing with the modified Arrhenius definition producing hydronium ions, it only ionizes one hydrogen at a time. The acid, as it goes through that process, becomes progressively weaker of itself. Okay? This doesn't mean, again, the more hydrogens, it becomes a really strong acid. It's just weaker of itself. And in fact, H3PO4, which has three hydrogens, is actually a weak acid. It's not on our strong acid chart that we learned about before. Now, you may be asked to show the steps of a polyprotic acid in water. So you're going to start by writing the formula for your polyprotic acid. This would be H2SO4. And you are going to, one step at a time, react it with water until all of the hydrogen ions are gone. Okay? So H2SO4, I could also write this as HHSO4. That's what H2SO4 means. One of these hydrogens, only one at a time, is going to donate to the water to form the hydronium ion. Remember, again, when the hydrogen is transferred, it carries a 1+ charge with it. So the hydronium has a 1+ charge, and I'm left with HSO4 with a -1 charge. Whenever something loses a hydrogen, its ion charge goes down by 1 because it's taking a 1+ with it. When something gains a hydrogen, its ion charge goes up by 1. It started at 0 and it's going up by 1 because it is bringing the H+ charge with H with 1+ charge with it. Okay? So you don't have to write this as HHSO4. I'm going to go back and actually put it as H2SO4. But I was just showing, again, maybe it's a little easier when you see it like that, only one hydrogen being transferred at a time. Now, HSO4 is still acidic. It's weaker than H2SO4, but it can continue to react. And polyprotic acids will continue to react with multiple water molecules until all of its donatable hydrogens are gone. So this hydrogen again can move over to water, again forming another hydronium ion. And once this H is gone, I'm left with SO4, now 2-, because as it lost a hydrogen, again, its charge goes down by 1. So from -1 to -2. Now, SO4 2- has no more hydrogens to donate. So it is done. The reaction steps are done. The number of steps and the number of water molecules it will react with depends on how many hydrogens it has. If it has 2 hydrogens, it'll react in 2 steps. Now we're going to write a net reaction from this. We learned a little bit about net reactions in the solution section of the unit. When you're writing a net reaction, we talked about how things like spectator ions can cancel, okay? The rule is if you have substances on opposite sides of the equation, they can cancel. So for example, I have HSO4 negative on the product side and HSO4 negative on the reactant side. Those can cancel. In these reactions, they're actually not called spectator ions. They're called intermediate species because they are produced in one step and then used up in the next. So the actual term for them is intermediate species. But then things on the same side actually add together. So my H2SO4 is actually reacting with 2 water molecules. They're on the same side, so I add them together. I'm producing 2 hydronium ions and the sulfate ion. Okay, so when things are on opposite sides, they cancel. When they're on the same side, they add together. Okay, so that is how we go through our steps of a polyprotic acid and show the net step. Again, the number of steps it's going to have in its initial reaction is depending on how many hydrogens it has. This had 2 hydrogens, so it reacted in 2 steps before we got to the net. If it had 3 hydrogens, it would react in 3 steps, and so on. Okay? Now, what about bases? We're going to get on to bases. Bases, if you remember, there's 2 types of bases you can have. You can have a strong base or a weak base, and they actually do different things in water. A strong base is an ionic hydroxide. Okay? If you have a metal bonded to the hydroxide ion, it is a strong base. Strong bases do not react with water. They simply dissociate. Okay? Oh, my notes are not in order here. There we go. So if your strong base has only one hydroxide ion in the formula, like NaOH, for example, it is called a monoprotic base. Now, weak bases, they react with water. Okay? Weak bases are anions and ammonia. If they react with water in only one step to produce only one hydroxide ion, then they are called monoprotic. So how do you know if they're going to react in only one step? If they have a -1 charge, they can only react with one water, and then they have no more negative charge. The negative charge is what makes them act as a weak base. Okay? So once the negative charge is gone, they can no longer be a weak base. Ammonia, you just have to memorize. It's going to accept 1 hydrogen to make ammonium, and that's as far as it's going to go. Okay? Now, back to strong bases. If your strong base, again, dissociates or has more than 1 hydroxide ion in the formula, it's a polyprotic base. So, for example, CaOH2, AlOH3. Those are polyprotic strong bases. They do not react with water. They would just dissociate. And so, for example, my calcium hydroxide, when it dissociates in water, it's going to form a calcium ion and 2 hydroxide ions, right? The balancing 2 coefficient, comes from the number of hydroxide ions in the compound. So strong bases, we do not react with water. They are ionic hydroxides. If they have only one hydroxide in the formula, excuse me, they are monoprotic. If they have more than one hydroxide in their formula, they are polyprotic. Now for a weak base, which again, those react with water, if they react in more than one step, they are called polyprotic. And again, how do you know if they're going to react in more than one step? If their ion charge is greater than -1. So -2, -3, and so on. Okay? So for weak bases, again, if they have a -1 charge or are ammonia, they are monoprotic weak bases. If they have a -2 or -3 charge, they are polyprotic weak bases. Okay, so bases, like I said, they kind of have 2 categories and they do different things, whether they just dissociate or react with water, depends if they're strong or weak. And that's 2 different kind of ways of how you look at them to see if they're strong or weak. Now, looking at a weak polyprotic base, okay, it's going to react in multiple steps just like the weak acids did. So for example, let's say we have CO3 2-. Now remember what a weak base does, or a modified Arrhenius base, as we learned in the first lesson. It takes a hydrogen away from water, a hydrogen 1+ ion. So when water loses its hydrogen, it's left as the hydroxide ion, and my CO3 is gaining an H to become HCO3. And like we said before, when something gains a hydrogen, its ion charge is increasing because it has a 1+ charge. So it's going to go up to -1 from -2. Okay? So that is step 1. Gaining 1 hydrogen at a time. Step 2, my HCO3 still has a negative charge, so it can react again. Polyprotic bases continue to react with water until all of their negative charge is gone. So if I started with a -3, it would react in 3 steps. Because I started with a -2, it's going to react in 2 steps. So what happens in the second step, as the hydrogen leaves the water and goes to the HCO3-1, my water again is left as a hydroxide ion when it loses its hydrogen, and the HCO3 becomes H2CO3, and it has no more negative charge because the +1 and the -1 balance as it gains that hydrogen. So it is no longer a base, and this is where the reaction stops. Okay, so it had a 2 negative, it reacted in 2 steps. Now again, we can write the net reaction between them, canceling anything on the reactant and product side. Again, remember they're called intermediate species in these reactions. They're produced in one step and used up in the next. Then adding everything together, and again putting together things that are on the same side. So I have 2 waters on the reactant side, so they add together. And you can write water as HOH or H2O. It doesn't matter how you write it. I like to write it when it's reacting with bases as HOH to show again that it's taking that hydrogen away, leaving water as hydroxide. Okay, so let me just keep it like that. I'll keep it as HOH. But whether you write it as HOH or H2O is completely irrelevant. It's the same thing. Okay, now I am producing 2 hydroxide ions and H2CO3. Okay, So again, for a polyprotic base, like a polyprotic acid, it reacts in multiple steps. A base continues to react until all of its negative charge is gone. Every time it gains a hydrogen, its negative charge goes up by 1. So from -2 to -1. And then from -1 to 0, there's essentially a little 0 there. Okay? So it continues to react until all of those negative charges are gone. All right. Lastly, before we finish, we're just going to talk about neutralization. We talked about neutralization reactions in the Science 10 review unit. But whenever you have a neutralization reaction, it is going to change the pH essentially to make it become closer to 7. So what's happening is my acid, which for example could be something like HCl, is reacting with my base, which could be something like sodium hydroxide. This is a strong acid reacting with a strong base. Okay. What's going to happen is a double replacement reaction. My acid is going to switch the hydrogen with the sodium in the base. So we're going to produce sodium chloride, which is the salt. The salt just means a neutral ionic compound. And I'm also going to have hydrogen hydroxide as my other product, which is water. Okay, so this is why it's called a neutralization reaction. Now, here's the thing. If I have a strong acid, that strong acid essentially exists as hydronium ions because it ionizes 100% into hydronium ions. And when I have a strong base, it ionizes 100% into hydroxide ions. Now, there's still chloride and sodium ions. We're just not showing them. This is the net reaction between a strong acid and a strong base. They're going to transfer a hydrogen from the acid to the base to make a water molecule and another water molecule. Okay, so again, what's happening is one of these hydrogens is transferring over here to make this become HOH, and this is left as H2O. So if I put that together, the net reaction between a strong acid and a strong base is making 2 water molecules, the net reaction. The sodium and chloride are still there. They're just spectator ions, so they're canceled out. Okay? So if we put that here, like I just explained, okay, the neutralization reaction, the net, we should call it, the net neutralization reaction between a strong acid and a strong base always produces 2 water molecules. Okay? Now, why is this important for us to understand? Because we have a lot of acids and bases in our society. When they're being traveled or transported, sorry, I should say, it's possible that there's a spill, right? Due to their reactivity and corrosiveness, we need to be extra careful with them when we're producing and transporting them. There are 2 ways that you can deal with an acid or base spill, and both ways are neutralizing it, okay? The first is just by adding water. When you add water, it dilutes the concentration. As the concentration gets lower, it becomes closer to a neutral pH. Okay, so if you ever in class, for example, spill an acid or base on your hand when we're doing a lab, I would just recommend you run it under water to neutralize it, to dilute it and wash away and decrease the concentration. Now, if you are going to neutralize it by adding an acid or a base to it, the opposite of what was spilled, you always want to use a weak acid or base so that you're not left with another hazardous situation. The problem with neutralization, though, on your hand, for example, if this were to happen, a spill on your hand, it's actually a very exothermic process and can release enough heat to cause a burn. So usually, like I said, if you spill on your hand, we're going to run it under water to dilute it rather than the neutralization process. Okay, and that, I believe, is it for this lesson. Thank you very much for watching.